Hello. In this video, I want to explain how we can calculate the Hamiltonian for a set of non-interacting particles on a lattice. These are the types of Hamiltonian that you'll be studying in the first of the assignments you have to do for the MTH 4332 module. The Hamiltonian function, h, is the function that takes in the microscopic state of the system and that returns the energy of that configuration. We can classify the Hamiltonians that we studied in a typical statistical mechanics course into four categories that are based on two criteria. The first of these two criteria tells us whether the system's constituent particles are sat on a lattice or if the particles are all independent. Hamiltonians where the particles are sat on a lattice are used to describe solid materials where there is symmetry. The Hamiltonians that treat each particle independently are used to describe gases. The key difference here is that the independent particle Hamiltonians are typically a function of the positions and momentums of all the particles. By contrast, the lattice Hamiltonians are usually a function of more abstract coordinates, e.g. particle spin. These coordinates usually bear some relationship to the particular problem that is being studied. The second criteria we can place on Hamiltonians is whether there are interactions between the particles or not. Strictly speaking, if there are interactions, that typically means that the Hamiltonian cannot be expressed as a linear combination of terms that depend on the coordinates of single particles. There are thus terms in the linear combination that makes up the Hamiltonian that are a function of the coordinates of at least two particles. We are going to start simple with this first assignment and study a system of non-interacting particles on a lattice. We are thus firmly in the quadrant in the space of Hamiltonians that has been indicated using a big blue circle. The fact that we are in this quadrant means that each particle will have a single coordinate. For a system of n particles, we will thus have a Hamiltonian that is a function of n coordinates as shown for h up here, where we have where the Hamiltonian is a function of the n x underscore j values. Each of the coordinates, the xj's in this expression, will be allowed to take a number of integer values in your project. Furthermore, because the particles are independent and identical, it will be possible to write capital H in this expression as a sum of terms that depend on only a single xj value, as shown here. Small hx underscore I will be given by a function that is something like this. This function means that each particle can be in one of three states: state 0, state 1, or state 2. If it is in state 0, its contribution to the energy is A. If it is in state 1, its contribution to the total energy is B, and if it is in state 2, its contribution to the total energy is C. Let's now suppose that the energies of states 0, 1, and 2, A, B, and C, are 1, 2, and 2 respectively. This means we are supposing that state 0 is the ground state for each particle and that there are two degenerate excited states, state 1 and 2. We can write a Python function to calculate the energy of any system of n particles with this Hamiltonian as shown here. Notice that this function takes one argument, state, as input. This variable state contains the state is an NP array that contains the states of the n particles in the system. Inside the function, we initially set a variable called n equal to 0. We then use a loop to iterate over all the particles, as shown here, to calculate the total energy. Inside the loop, we have an if statement that uses the state of the ith particle to determine its energy. The energy of the ith particle is then added to the variable n that will contain the total energy. Finally, the variable n is returned from the function so that it can be accessed by the code that called the Hamiltonian function. Hopefully, this is relatively straightforward. Try the exercises now and see if you can use the contents of this video to implement a few Hamiltonians yourself. Thanks for your attention.